All right. So where we have been. So far, some of the main things that we have talked about is the necessity of good sound sampling methods. So having to make sure that if you are collecting data, that you're collecting data preferably in a good, simple, random sample, where every set of the same size has equal chance of being selected. So if you've got good data that you've brought in, some of the common measures of your characteristics of data are some of the things we've talked about as far as finding the center, talking about the variation, talking about the distribution, talking about how it changes over time, and talking about variance. And variance is one of the things we talked about during Chapter 3. So those are just giving us some different information about what that data looks like. The main ones we've looked at as far as finding things was when we talked about the center. One of the main things we use is the mean, although sometimes the median is another really good way to be able to talk about that middle, and sometimes the mode. Hopefully, if you've got a good normal distribution, mean, median, and mode should all be pretty similar to one another. And then we've also looked at the standard deviation, talking about how much it varies, whether or not you've got a large standard deviation or a small. Our standard deviation, I think on this test was 19%. And so having a standard deviation of 19% means we had a really big variation between our grades, that we were not having all the grades super close to one another. And so it talks about how much those things are spread out. We talked about the difference between descriptive statistics and inferential statistics. Descriptive statistics is what we have already been doing. That is when we are trying to describe numerically some of those important characteristics of a known set of data. When we were finding the mean, the median, the variance, all of those are describing the data that we have. On the other hand, inferential statistics we haven't really gotten into yet, it's coming, is to use the sample data to make inferences or generalizations about an entire population. So that's something that we're going to go into, not yet, but soon, will be one of the things we're talking about. This chapter, some of the main things we're going to talk about is the rare event rule for inferential statistics. And I guess we do a little bit of inferential in this chapter, now I think about it, which is if under a given assumption, the probability of a particular observed event is extremely small, we conclude that that assumption is probably not correct. Good example, if we're flipping coins. If I'm talking about trying to flip a regular coin, two-sided, nice, normal coin, if I plan on flipping it and I think I'm going to get tails every single time I do it. If I'm going to do that once, probability of getting tails is a good chance that I might be right. If I'm planning on doing it 100 times, is it very likely that I'm going to get a tail every single time if I've got a normal coin? So the probability is so extremely small that if I came to the conclusion and said that I had tails every single time I flipped the coin, there's probably something wrong with what I've been doing. And you guys would definitely, the probability of that happening is very, very small. And so to think that that's a possibility is unlikely. And so there's probably something about my assumption was not correct. Probably the fact that I had a good, simple, or good, normal coin that is not weighted somehow, or not a coin that's got two sides that are both tails or something like that that's causing it to be a problem. And so there's something wrong with my original assumption, more than likely, if I can get 100 tails in a row. Statisticians then use that rare event rule for talking about your inferential statistics. So that's where we're heading in this chapter. So this chapter is going to really be focusing a lot on probability. First of all, this section here is going to present the 3 approaches to finding the probability of an event. Doing some of our definitions first. An event is any collection of results or outcomes of a procedure. So if I'm flipping my coin and I'm collecting how many times I get heads, how many times I get tails. So that would be collecting that information. That would be my different events, would be flipping my coin or rolling a dice and counting how many times I roll a dice and get an even number. Could be another example of trying to look at different events. A simple event is an outcome or an event that cannot be further broken down into smaller components or into simpler components. Flipping a coin, there's no simpler thing than counting the number of tails that you get. You can't break that down any further. Rolling a dice and counting how many times you get an even number. Again, that's as simple as those events could get. So those are good, simple events. If we were to roll a coin or flip a coin and draw a card at the same time, that one's not a simple event. And trying to figure out if we can get a heads and an ace at the same time. Well, those are events that can get broke down small or into simpler events because we can figure out what the probability of getting an ace and what the probability of flipping the coin and getting a tail, to where we can make those simpler events as we do it. Your sample space is all your possible simple events. So if I'm rolling a coin, I don't know why I keep wanting to roll a coin, rolling a dice. If I'm rolling a dice, my simple events I could be rolling a 1, 2, 3, 4, 5, or 6. So those would be my different simple events. If I'm flipping a coin, then I can have my simple events be its heads or its tails. Drawing cards. We'll come back to cards in a little bit. Your sample size then is the count of the sample space. And if I was rolling my coin or rolling my dice, and I was counting how many times were even and odd could be my 2 simple events. And then I would only have 2 options even though I had that 6-sided dice. Questions on the definitions of any of these so far? Going with our notation then, capital P denotes a probability. A lot of times we talk about the different specific events as A, B, or C. They are capital letters when we talk about the different events that can happen. So P of A denotes the probability of event A occurring. Or it might be, A might be the probability of rolling a 1, and so it might be the probability that you roll a 1. We'd find with that probability of having that, which is going to be just a simple 1 out of 6. Will be the probability of rolling a 1. But that event A represents whatever that event is that you're talking about. Now, there's different ways of finding the probability. And I mentioned there's 3 different possible ways that we can go about finding probability. One way is the relative frequency approximation of probability, which is to conduct or observe a procedure and count the number of times event A actually occurs. Based on these actual results, P of A is approximated as follows. The number of times A occurred divided by the number of times the procedure was repeated. So if we were trying to do where we're flipping a coin, and I had everybody in here flip a coin 10 times and count how many heads we had, then we could go through and count how many people actually flipped it and got heads out of how many different times we were flipping the coin. So we got 8 of you guys that are in here today. No, we got 9 of you that are in here today. So if we had everybody doing it 10 times, then we would have 90 different attempts, and we could just count how many different heads we had, and however many heads that was, how many heads there were, it'd be that many out of 90. And that would be just going through and doing the relative frequency approximation of probability. Now, would I anticipate, or would you expect that it will always be exactly 45 out of the 90 that's going to be heads? No, because we're doing this actual experiment where we're looking at doing it. When you flip a coin, it's not every other time. It always flips back and forth to be heads and tails. And so it probably won't be exactly 45, but we do expect it to be around half the time. And so this one's not going to be, this is just one of the methods that we can do for approximating those. Questions there? The second one is your classical approach to probability. This has to have things that are equally likely outcomes. So flipping a coin, it's equally likely that you get a heads or a tails. Rolling a dice, getting a 1 through 6 are all equally likely. You assume that a given procedure has n different simple events and that each of those simple events has an equal chance of occurring. If event A can occur in S of these n ways, then the probability of event A happening is S over n, or the number of ways A can occur divided by the number of different simple events. So the probability of getting a heads is 1 out of 2. Because there's one head out of the 2 simple events. What would be the probability that if you're on a dice that you're going to roll a 2 or a 3? How many different ways can I roll a 2 or a 3? Not trying to be tricky. On a regular die, how many ways can I roll a 2 or 3? 2 chances. I got roll a 2 or I roll a 3, so 2 different ways. How many different sides are there on a die? So there's 6 different options. So the probability that I'm going to roll a 2 or a 3 is 2 out of 6, or 1/3 of the time I would anticipate rolling a 2 or a 3. And so that's just looking at that classical approach. You're looking at each event being equally likely, and then you just count how many ways you can get that out of how many different options there were, how many different simple events that we could have gone. The other is the subjective probability. This is, P of A is the probability of that event A is estimated by using knowledge of the relevant circumstances. In other words, this is your best guess. If I was going to be trying to look at the probability that the next car that comes down the road is red, well, there's not really a great way that we can just guess what the net probability that the next car coming down the road is going to be red is. But you could just use your best guess of, from what you know of how many people you know that have red cars out of all the cars you're familiar with. Or we could even go with our best, or an estimate, or that first method of doing things, where we do the experiment and go out to the parking lot and count how many red vehicles there are out of all the vehicles there we could be, to give us even a better subjective probability, which would be moving it into more of the experiment with it method of doing things. But you can try to figure out your best guess. What's the probability that, I don't know, next time that we come to class that I'm going to be wearing black? Since I wear black frequently, you could probably guess pretty high on probability that one's going to happen. But just a subjective probability, your best estimate is what you're looking at doing on those. Questions there? Questions on what the differences are between the three? All three of these are ones that I'm sure you've just sort of naturally moved yourself into doing before, but not necessarily always considering the notation and some of that kind of things on these. Trying to see if I had any other notes that I wanted to make sure. So, I thought I had some more examples of some stuff, but I want to make sure we talk about a couple of these. If we were talking about the relative frequency approximation of probability, what if my question was, from here, if we wanted to go with the probability that somebody's wearing black? How could I use this method to try to figure out the probability that someone is wearing black? Okay, so if we did the probability that we had somebody in class wearing black, as we count, just raise your hand if you think you're wearing black. Okay, so 1, 2, 3, 4, 5, 6 people wearing black out of, we've already counted of 9 people in here. So probability somebody's wearing black, 6 out of the 9, or probability of 2/3. I'm trying to remember if it's this time or a little bit later that we talk about the different things with cards. I do want to mention cards because I use these references frequently, and I want to make sure everybody's familiar with a deck of cards. Regular deck of cards has how many cards? Okay, there's 52 cards in a deck. Out of the 52 cards in a deck, what are the different suits? How many suits are there? Okay, there's 4 suits, and they are? Okay, so those are different things. Hearts and diamonds are red, clubs and spades are black. What are the different face values you can have? 10 through 2. Sorry, I'm kind of going backwards. It says go from the highest value to the lowest. I'm not counting jokers, which would move it up to 54. But I'm not going to worry about counting jokers in ours. It makes things a little easier when we're doing the probability. So each one of these suits has how many values? So there's 13 cards in each one of those suits. So that's where the 13 times 4 gives you the 52 cards in your deck. So I know some of you are more familiar with the deck of cards than others, and I've made the assumption people knew those, and I wanted to make sure that I didn't make that assumption because it confused somebody in the past. So if I wanted to find the probability, and let's do, this is rule 2, so this is a good one for this, probability that I was going to have an ace. Okay, there's 4 aces in the deck because there's an ace in each one of those suits out of the 52 cards. And so we're going to get 1 out of 13 of those are going to be an ace. Questions on using the classical approach to probability? Reduce fractions? Yes. Yes, always reduce fractions. Okay, the law of large numbers. As a procedure is repeated again and again and again, the relative frequency probability of an event tends to approach the actual probability. So, if instead of having each of you guys flip a coin 10 times and count how many heads out of how many tails, so that we had, first of all, just from your own personal 10 flips, you're going to have a wide range of different kinds of things. You might get one person who only gets 1 tail out of all this, somebody else that gets 8 tails. It's going to be all over the board of how many different tails each of you will get. And so it's not really, for just 10 flips, you're probably not going to get a probability that's necessarily close to 1/2. But then if we had everybody doing it, we had 90 flips, it should be getting closer. If instead of having each of you guys do it 10 times, if I had you each do it 100 times, so that we had 900 flips, we're going to be getting closer to the true probability of 1/2. If I had each of you do it 1,000 times, so that we had 9,000 different things, again, it's going to get closer and closer and closer. Having it being off a little ways, well, if you're off, if we're looking at having 9,000 of these, if I do 9,000 flips, I would expect, if it was a perfect example of stuff, we're estimating that we'd have 4,500 out of the 9,000 that would be heads or tails, whichever one you're going to go with. Well, if you guys are off by 100, which off 100 of them sounds kind of large, but if you take 4,400 and divide that by 9,000, I can't do that one in my head. You get a probability of 0.488 repeating. So you're getting a probability that's really close to 1/2. Even though, having it being off 100 sounds large, that law of large numbers is saying as you do this experiment more and more times, it's going to get closer and closer to what that true probability is. And that is going to be a rule that we're going to really depend upon being able to use and expect things to be the case. Which is where a lot of that probability has come from, is because you've recognized that when you've done these experiments enough times, that it tends towards what you have as that expected probability. All right, when we talk about probability limits then, first of all, always express probability as either a fraction in reduced form or a decimal number that's going to be between 0 and 1. Now, why would probability have to be between 0 and 1? What does a probability of 0 mean? Okay, it's not going to happen. It is absolutely impossible. So when we're looking at the probability of something that is absolutely impossible, that means the probability is going to be 0. The probability that you're going to walk away tonight without any statistics homework would be 0, because it's pretty much guaranteed, since we've started in on this lesson, that we're going to be having an assignment tonight. I can email it to you. Don't worry. You'll have one, Erin. So the probability of something that cannot happen is 0. Well, what's the probability of 1 mean? It's going to happen. So probability that you will have homework is 100%. So that's telling you it's going to have a probability of 1 that is guaranteed to happen. So when it's certain to occur, your best probability you can have is 1. Probability that you're going to flip a coin and you're either going to get a heads or a tails. Well, if you flip a coin, it's either going to land on heads or it's going to land on tails. You're not going to be able to get a coin to flip and just land on its edge and not have anything. I know I'm challenging you, aren't I? Goodness. So as you're looking at doing these, you're looking at having that probability of one or the other being guaranteed is going to be that 1. So then everything else has to land somewhere in between. So for any event A, the probability that A occurs has to be between 0 and 1 inclusive. Inclusive means including those endpoints. So you can get a probability of 0, you can get a probability of 1, or a number in between. Leave your probabilities either as a fraction, and I prefer reduced fractions most of the time, unless your numbers get, if we're having 221 out of 564, that doesn't tell me much when those numbers are strange. Probability of 1/3, we all can recognize what that means. But a weird probability like that, it's better to turn those ones into decimals. But most of the time, we'll just leave things as fractions is usually an easier way to do things. Another way to express that it has to be between those two is that the probability that A occurs, 0 is less than or equal to probability of A, which is less than or equal to 1. It's another way of saying it's between 0 and 1 inclusive. Complementary events. The complement of event A, denoted by A bar, consists of all outcomes in which the event A does not occur. So, if A is that we are going to roll a 2 or a 3, what is A bar? Means I'm not going to roll a 2 or 3, which means I'm rolling what? So, first of all, what's the probability that event A occurs? What's the probability I roll 2 or 3? Okay, 2 chances out of the 6 options, which reduces to 1/3. What is the probability that A does not occur? Okay, it's going to have 4 out of those 6, which is your 2/3. What do you know about the probability of A and A bar together? They have to add up to be 1. If they're going to be complementary events, then the sum of those two probabilities have to add to be 1. It's either that it happens or it doesn't happen. There's no in between those two things. So either A happens or A bar happens. One of those has got to be true because those are complementary events. Oh, I didn't remember I had an example just like what I was just saying. Let's just change this one. Let's go with, instead of having the dice, let's go with cards. And what's the probability that we're going to get a king or a queen in a deck of cards? Okay, we're going to have 8 out of 52 because you have 4 kings and you have 4 queens. So you got 8 out of 52, which reduces to being 2 out of 13. Each suit has an option of a king or a queen out of the 13 options. So what would A bar look like? What was that? That will be the probability of A bar. What is A bar, though, in this case? If you're not getting a king or a queen, you're getting ace, jack, and then the 2 through 10. So you've got 13 different options on what you have there. I'm sorry, not 13, 11 different options out of what you've got there. So the probability that A happens is your 11 out of 13. Questions there? Probably would have been easier if I would have said the probability that we had a club, and it would have made A bar faster to write. All right, when we're rounding these then, When expressing the value of a probability, either give the exact fraction or the decimal, or round off the final decimal results to 3 significant digits. So when we're talking about trying to round these, if it's nice and exact, 2/13, leave it as 2/13. It's kind of easy to recognize. If you felt the need that you had to express it as a decimal, round it to 3 significant digits. What does it mean to be significant digits? What do you mean by they have a value? Okay? Some zeros count, some zeros don't count. Which zeros don't count? So let's go to the easier part. Okay. We're going with 2 different sides. Both of you guys let me ask it this way. Which one of these 2 zeros counts, the first one or the second one? Okay, you guys are saying opposite. That's what I was afraid of. This 0 actually counts. This 0 right here is telling me that place value actually is nothing, that you have a 0 in that value. This one is just a placeholder that's saying, I need to get over here to the hundredths and thousandths place. This 0 here is something I would have to, it's just helping me get to that spot. Now, in that case, an easy way that I kind of can remember which one's which is if you were going to put things into scientific notation, this 0 would disappear. This would be 2.5 times 10 to the negative 2. Since that 0 would disappear, it really wasn't important. This 0 actually still should stay. This would be 10 to the negative first. That 0 should stay because it's saying that place value, the 10,000th, no, thousandths. The thousandths place value actually has 0 in it. It's telling what the value is in that spot. And so that 0 truly is important. So when we talk about 3 significant digits, it's saying ignoring the zeros in the front, put 3 decimals after, 3 place values after that. So if I was wanting to have, I'm trying to think of a good value to give you as a rounding. If we had 1/15th, 1/15th is 0.0, and then it's got the 6's repeating forever. If you're rounding that one to 3 significant digits, then this original 0 would not count. So this is approximately equal. It's not very good approximate. It should have little squiggly lines for approximately equal. There we go. And so we would keep the 0 and then 3 decimals after that. So it would be the 0.0667. Questions there? Was anybody still writing my example before I erase it so we could read what I had underneath it? So keep the value exact if possible. 1/3 is best, but if you have to round it, then we would round 1/3 to 0.333. All right. Test looks like it's going to fall on February 25th. This will be your guys' homework for this section. Try to work on your test corrections. Have them for me on Wednesday. Like I said, I'll take the answer key over to the ARC shortly. And I'll see you guys on Wednesday.